Here is a question. Read it carefully and think about the answer. Let us solve it step by step. Let us begin solving this step by step. The starting material is 4-methylcyclohexyl, methanol, a cyclohexane ring with a methyl group at C4 and a CH2O, primary alcohol, group attached at C1 via a CH2 linker, i.e., the CH2O is exocyclic. Moving on to the next step. PCC oxidize primary alcohols to aldehydes and secondary alcohols to ketones. With excess PCC, the primary CH2O is oxidized to an aldehyde, ChO. The ring has no secondary alcohol, so the only oxidation is CH2 ChO. However, looking more carefully at the starting material structure, it is drawn as a cyclohexane with a methyl at top, C1 of ring, and a CH2O at C2 of the ring. With excess PCC, the primary alcohol, CH2O, is oxidized to an aldehyde, ChO. So, A is equal to 4-methyl-cyclohexane carbaldehyde, the ChO is exocyclic, with a methyl group on the ring. Actually re-examining, the structure shows a cyclohexane ring with methyl at C1, top, and CH2O at C2. PCC, excess, oxidize the primary alcohol to aldehyde. Product A has both a ring ketone. No, there is no secondary O on the ring. So, A is equal to aldehyde, 1-methyl, 2-cyclohexyl, acetaldehyde equivalent, the CH2O becomes ChO. Wait, rereading, excess PCC could also mean it converts an aldehyde further only if there's a secondary alcohol nearby, since there's only a primary alcohol present, A is equal to the corresponding aldehyde. Moving on to the next step. Reaction with ethylene glycol, 1-equiv, H plus gives, B. This is acetal protection. With 1 equivalent of ethylene glycol, 1-carbonyl is selectively protected as a cyclic acetal, 1,3-dioxylane. Since A contains only 1 carbonyl, the aldehyde from oxidation of CH2O, that aldehyde is protected as a 1,3-dioxylane acetal. So, B is equal to the aldehyde is protected as cyclic acetal, and the methyl group on the ring remains. Actually, let me reconsider the starting material more carefully. The structure shows a cyclohexane ring with a methyl group at C1, top of ring, indicated by the line going up, and a CH2O group at C2. With excess PCC, primary alcohol aldehyde. So A is equal to 2,1-methylcyclohex, 2-vial acetaldehyde. More simply, the CH2O attached to the cyclohexyl carbon becomes ChO. A is an aldehyde. And for the final step, B with CH3NGBr, then H3O plus gives, see the Grignard reagent CH3NGBr adds to the remaining carbonyl. But in B, the aldehyde is protected as acetal. So what carbonyl does CH3NGBr react with? This means A must have had 2 carbonyls, the aldehyde from CH2O oxidation and a ketone from some ring oxidation, and B is the monoprotected product, aldehyde protected, ketone free. Then CH3NGBr adds to the ketone to give a tertiary alcohol. Re-examining starting material, cyclohexane ring with CH2O at 1 carbon and a methyl substituent. If the carbon-bearing CH2O also has an H, secondary position on ring, excess PCC would oxidize, 1, CH2O ChO, aldehyde, 2, the ring CH-bearing CH2O C is equal to O, ketone. So, A has both an aldehyde, exocyclic ChO, and a ring ketone. With 1-equiv ethylene glycol H+, the more reactive aldehyde is selectively protected as acetal. B is equal to acetal protected aldehyde plus free ring ketone. CH3NGBr adds to the ring ketone in B to give tertiary alcohol. C. The ketone C is equal to O on ring reacts with CH3NGBr to give a tertiary alcohol with methyl added. After H3O plus workup, C has ring with C1 or CH3 tertiary alcohol, quaternary carbon, and C2 still bearing the protected aldehyde, acetyl. NaBH4 is a mild reducing agent. It would not reduce an acetyl. However, the acetyl must be hydrolyzed first. But the question says NaBH4 directly. Under the reaction conditions, or perhaps during workup, the acetyl hydrolyzes back to aldehyde and NaBH4 reduces the aldehyde to primary alcohol. So, D has ring C1 with OH and CH3, tertiary alcohol, from Grignard addition and an exocyclic CH2OH, from reduction of aldehyde. The methyl group originally at C4 of the ring was actually the methyl at C1 which became part of the tertiary alcohol after Grignard addition. Final product, D, a cyclohexane ring where one carbon bears OH, CH3, methyl, and CH2OH substituents i.e. 1-methyl, 1-hydroxymethyl, cyclohexane, 1-ol. But this is a quaternary carbon with OH, making it 1-hydroxymethyl, 1-methylcyclohexanol. This matches option B, cyclohexane ring with C1 bearing OH and CH2OH and methyl group, 1-methyl, 1-hydroxymethyl, cyclohexanol. Why other options fail? A shows an open chain CH or CH3 side chain which would require different chemistry. C and D show 1-hydroxymethyl, cyclohexanol without the methyl group on the quaternary carbon. Option B correctly shows the methyl group on the same carbon as OH and CH2OH, consistent with original ring methyl. C4 position on original ring actually was on C1 of ring bearing CH2OH, making it a tertiary ring carbon, being converted to quaternary carbon after Grignard addition of CH3, then acetyl deprotection and NaBH4 reduction of CHO to CH2OH. Therefore, the correct answer is B. Therefore, the correct answer is option B.